All right, in this video, we're going to talk about correlation and correlational studies. So we saw on that the slide in the last video, this slide describing different types of research designs, that correlational studies can be very crude and basic up here, right? And those crude, basic correlational studies are going to be considered to be pre-experimental. But correlational studies can also sometimes be quite sophisticated and in fact be considered quasi-experimental designs where researchers might actually have more information on their groups so that they can somewhat control for some of the built-in confounds that can otherwise go along with correlational designs. But as a general matter, correlational studies just look at the relationship or concurrence of two variables on some dependent measure. Okay, so you just measure two or occasionally more, but starting with two variables. And then you see if, well, when variable 1 changes, does variable 2 change also? And if it does it change in the same direction as variable 1 or in the opposite direction to variable 1? And of course, the answer might also be that it doesn't change at all. And these three possibilities are known as positive, negative, and zero correlations. Okay, so we've got those illustrated here on the slide. So this slide I like because it has a real life example. So this is illustrating positive, zero, and negative correlation, all concerning variables that have to do with cars. Okay, so starting here on the left, we see there is in fact a negative correlation between auto mileage and auto value done on this axis. This makes sense, right? The more miles a car has on it, the lower the value is going to be. Okay, moving on, in the center, we actually see essentially a zero correlation, no correlation between auto color and the value of the car, right? And then lastly, we're going to see the example of a positive correlation. Positive correlation here between auto insurance cost and auto accidents. All right, the more accidents a person has, the more their insurance is going to cost. Maybe some of you have personal experience with that. Hopefully not, but it can get very expensive. Okay, so a classic example of a positive correlation is between smoking and lung cancer. And this correlation is actually seen both with time and quantity, right? The more a person smokes and the longer a person smokes, the higher the risk of lung cancer. So an example of a negative correlation is the relationship between age and committing violent crimes. Negative correlation between age and committing violent crimes, assuming a very important thing, assuming that you don't start measuring until sort of the mid to late teens. Because as we age, overall, we commit fewer crimes. But we have to note that if we actually started from infancy on up, we'd get a very uneven shaped correlation, right? Because obviously crime commission starts at 0 in infancy, doesn't rise until around the early teens. Then it's going to reach a peak in the late teens and early 20s before going back down again. Okay, on this slide, is a cartoon that illustrates this truism in science that correlation does not imply causation. So it's definitely true that classically speaking, you can't automatically deduce a causal relationship between variables that are correlated. So go ahead, if you haven't read this cartoon yet, please pause the video and read it. Okay, so this idea that you can't deduce a causal relationship, even when you have correlation, that's true, right? Because let's say you have a positive correlation between two things, like we see here. We have a perfect 1.0 correlation. So now this correlation can either be the case because variable A rising over here causes variable B to rise, but it could also be that it's variable B rising that causes variable A to rise, or it can even be the other way around. I mean, or a third possibility, which is that some third variable X is actually causing both A and B to rise, like, for example, our third variable, hot weather, causing increases in both ice cream consumption and drowning. So getting back to pick on tobacco companies again, tobacco companies always insisted on this particular point in critiquing smoking research. For decades, they tried to argue that we just didn't know for sure if smoking was a cause of lung cancer just because the data were there showing a correlation. Another example we already talked about is that if we have data that violent people watch more violent television than average people, we don't know which one might have caused the other, or in fact whether there's any causation at all. Does watching violent TV lead to violent behavior, or does being a violent person lead people to seek out violent TV shows? Or is there some third factor that causes both, like exposure to electromagnetic fields, or being a diagnosable psychopath who lacks normal emotional feelings, leading to both acting violently and choosing to watch violent television? Of course, all of those, in fact, might be even partially true, which would make it even more complicated. So this inability to imply causation from correlation can be overstated. And remember that it's not always a problem, right? We're not always concerned with cause and effect relationships in science. Remember, if you just want to make predictions, then directionality and third variables, not always a problem, as long as you have really solid data. In the example about violence and watching violent TV, if any of those possible causal paths were true, the ones that I mentioned on the last slide, well, if you know that a person watches a lot of violent TV, that still helps you predict, at least to some extent, whether he or she will be violent. Same thing with ice cream sales and drownings. So if you're making predictions using correlation, you want to know not only whether there's a positive or negative correlation between the populations on the specified measure, but you want to know, well, what is the strength of that relationship? Because a stronger correlation is obviously going to give you more accurate predictive power. So this, of course, is statistics. So, of course, there's going to be an equation. The most commonly used value for correlation coefficient is the Pearson's product moment coefficient of correlation, sometimes referred to here as the Pearson's R. And here's the equation for that, which mercifully we do not have to understand at all. But certainly the general things that we do need to know about correlation coefficients are here on the slide. Okay, so this correlation coefficient number, it's a number that indicates, well, what is the relationship between two or more paired variables or two or more data sets? It's usually listed in research studies as the lowercase letter r or the lowercase letter p sometimes, so watch for that. What else do we need to know? Well, the number for the correlation coefficient, it's always going to range from a -1, that would correspond to a perfect negative correlation, to a +1, which would be a perfect positive correlation, right? So a perfect correlation, just to operationally define what I mean here, a perfect correlation of positive or -1 indicates that for every unit of increase or decrease, of course, if it's a negative correlation, in one variable, there's an increase or decrease in another variable. Okay. Here on this slide, we see a perfect positive correlation, perfect 1.0 correlation. Here we see a perfect negative correlation, perfect -1 correlation. All right, so here we see an example of a -0.3 correlation. Okay, often when you see data illustrated with a correlation coefficient, you'll see a diagram very similar to this. So this is called a scatter diagram, which actually shows all of these individual data points from your study on your diagram. So the way you get, well, how do you get from all these values to this nice, neat line that you can measure? Well, how you do that is by using a mathematical formula where all of these individual data points get factored into the correlation coefficient equation to give you the value for R. So nowadays, this is going to be done completely automatically by a computer after data values are inputted. So you can certainly understand here, well, why 0.3, or here in this case, negative 0.3. Well, this is considered a pretty low correlation, and that makes perfect sense because when you look at how scattered these data points are, you know, you might not even know just by looking at them that there's any correlation at all. So 0.3 is going to be a fairly weak correlation coefficient. This slide I really love, showing the scatter diagrams for data ranging from 0 correlation up here at the top, down here at the bottom right to almost perfect 1.0 correlation. So this slide gives you a great sense of what the values between 0 and 1 correlation kind of mean in this context with regard to your data. All right, next we're going to look at some real life examples. So here what we have is the correlation scatter plot of height and weight in humans. So you can see that there is a positive correlation here shown by this line, but certainly not a perfect correlation, right? It's nowhere near, you know, that perfect 1.0 correlation. Obviously, there are many shorter people on the heavier side, you know, up here, shorter people on the heavier side there. There are some taller people, say up here on the lighter side, right? So those outliers are going to affect your correlation coefficient and bring that coefficient down a bit, lessen your correlation that you can claim. Here we see a scatter plot looking at fitness level as compared to percentage of body fat. Okay, so we see generally there's a negative correlation here. So, you know, that indicates that the higher your percentage of body fat, generally you would predict that your fitness level would be lower. But we see again that it's not a perfect correlation by any means, right? There are some people with low body fat who score low on a measure of fitness, you know, lower body fat here, but scoring low on a measure of fitness. There are some with a high body fat measure of fitness, like this person up here, pretty high body fat percentage, but also scoring pretty high in fitness. So those outliers, again, pulling the correlation down from a pure -1 correlation coefficient. So what we're learning here, I think you're seeing illustrated this phenomenon that outliers really can drag your correlation coefficient down with your data. This one, definitely a little bit depressing, showing that as people age, their average height decreases. So age is slightly negatively correlated with height. And so I've often actually wondered whether this particular scatter diagram reflects the actual shrinking that happens as our cartilage breaks down and our spinal discs degenerate, or maybe whether it might also include the fact that men generally die younger than women and are also taller, so that there's a higher percentage of women represented in the older ages reflected on this chart. So I'm not sure about that because I can't remember where I got all these correlation charts. But, you know, frankly, not being able to remember where I got the correlation charts, probably also a function of age, as in the older you get, the worse your memory is. That would be another depressing chart altogether, I guess. Okay, so here's a data set for which you might calculate a correlation coefficient, but you can see that you don't, in fact, have anything approaching a neat linear relationship here. So your coefficient is going to be lower than it would otherwise be, and in fact, it may not be a very good way to describe your data, certainly not on its own. So what this graph shows is correlation between weight and fitness level, similar to the other one where we were looking at body fat percentage. You can see that fitness is actually lower, right? Lower at these very bottom weights, all right? And at first it increases a little bit with increasing weight before then going fairly consistently downhill as you get over a certain weight level. So this might reflect the fact that sometimes very thin people don't have much muscle mass. That could certainly affect their fitness score. So again, you might calculate a correlation coefficient here, but you wouldn't want that to be the only way you described this otherwise very interesting data set. This one also very, very interesting for test takers. So you have some data that can really tell you something, right? But it's not at all linear data. So really you would not even want to calculate a correlation coefficient. It's not going to be a good statistic to use to describe the data set. In fact, it's probably going to be close to zero anyway. But what these data do tell us, right, is that test performance graphed here, actually improves when a person has a certain amount of anxiety, right? Maybe that translates into an adrenaline rush that might help you with focus and speed, right? But as you can see on the graph, anxiety above a certain level does start to negatively affect test performance. On the other hand, just because data isn't perfectly linear doesn't mean the correlation coefficient is meaningless. Here we see our class mascot, Abby the Wonder Dog. Many of you probably know this generalization that 1 year of a dog's life is supposed to be equivalent to about 7 human years. That is going to be reflected here in this graph on the left. That's if it was actually sort of 7 human years for 1 dog year, it would be sort of a perfect correlation there. All right, but in fact, what we see in the graph on the right, okay, this is actually a more accurate description showing that the ratio of human years to dog years is higher here in the first couple of years of a dog's life and then settles down more into that 7-to-1 rough ratio. Then in fact, later on in the dog's life, the ratio drops a bit. So not actually a neat linear relationship, but a correlation coefficient is still going to be a meaningful statistic to describe a graph like this. Okay, the other thing I wanted to point out is that outliers in your data can severely affect the correlation coefficient calculation. So the 3 images on this slide, I think, illustrate this really well. So up on the top left, okay, we see that all but one of the data points there seem to line up pretty well for a high correlation coefficient, right? So you'd think that it would be high up here because look how well these line up, except, look at this 1 point down there on the bottom. Because of that one outlying data point, the mathematically calculated coefficient is only around 0.2 to 0.3, as you see on the slide, depending upon which formula you use. So now on the top right image, the far right image, you see the dramatic effect of adding in and taking out that outlying data point. So without the outlier, the coefficient is going to be a relatively high 0.7 in this data set. But now over here, if you add this outlier back in, look how it drops the correlation all the way down to 0.4. The bottom series of images shows the effect of, in fact, adding 2 different outliers. So we see on the left, the data points shown give us a nice correlation coefficient of almost 0.9. In the middle, adding this outlier up here on the left, okay, pulls the coefficient down to 0.37, and the one on the right I think is really interesting because we have an outlier that is removed from the other data points, so it is an outlier up here, this guy, okay, but it falls roughly on the linear path that the other points form. So that outlier actually increases our coefficient all the way up to that really, really high 0.97. Okay, this slide shows a couple examples of samples of students. So our samples here are just groups of students. So on the left here in each table, we see the student's verbal SAT score, right? And on the right, we see the student's grade point average for each of our two data sets. And on the right here, you see these data sets graphed. So the first sample of student data graphs out really nicely here. You see this very high 0.94 correlation between a verbal SAT score and GPA. But down here in this group, the first thing to notice is that all of the data here are the same for the students. See this? They're the same as the graph up here, except for this one data point down here. When we take Corbin, right, the student with the highest verbal SAT score, and drop his GPA down from 3.9, which it is up here in this graph, all the way down to 2.2, he becomes over here on the graph an outlier, and see how his data point pulls that correlation coefficient all the way down here to 0.32. So with the outlier, the correlation coefficient is not a good statistic to use to really convey the import of the data, right? Because for the majority of the students, majority of them, you know, this is really well correlated, right? So the addition of this data point sort of makes the correlation coefficient sort of a less useful statistic to use to describe this data set. And the last couple of slides here are very interesting to law students because they have to do with correlation between various U.S. news variables and bar passage rate. So we see there's a high positive correlation of 0.84 here between peer assessments of law schools and bar passage percentage among students. Also a high correlation between lawyer and judge rankings versus bar passage rates. And in fact, even higher correlations than that, right, with the GPA and LSAT scores are related to bar passage rate. So down here, though, at the bottom of the chart, these last two numbers, you see the negative correlation coefficients associated with acceptance rate and student-faculty ratio, right? So here, the more selective a school is, the lower percentage of applicants it accepts, and the higher the bar passage rate, right? So those two are negatively correlated, right? It's more selective, it accepts fewer students, and that's associated with bar passage rate going up, okay? And then down here, the higher the student-faculty ratio, the lower the bar passage rate. So that means basically more professor attention seems to be associated with higher bar passage percentage. Okay, that's going to be the end of this video. So I will see you in class on Monday.